I guess not for you guys. All right. So, to recap where we are, we started off saying calculus is all about the rate of change. Then we spent an episode just going over how the rate of change, when it's over really tiny distances, that's what calculus is all about. That's what calculus loves, tiny distances. Yeah, that's calculus. That's calculus's thing. And when we talk about the concept of a derivative has two definitions. It's the rate of change at one point. So, for example, this point right here, what is the rate of change right here? Yeah. And the other definition of a derivative is how much does the output change with a tiny change in inputs. For example, no matter how many times I scroll my scroll wheel, will it zoom in to the level I actually want? That's a derivative right there. So you bump this lever input, how much does the output change? Now, afterwards, we talked about the theoreticals, the memorization, boring, I know, I'm sorry. Uh, there's this very important thing called the power rule, which is a little bit hard to learn because of this binomial theorem. If it weren't for that, I would teach it to you, but I showed you the formula. And what it does is it lets us go from a function like, let's say, f of x is equal to x squared, where you have the input and then you have the output that we graphed up here. It lets us go from that to f prime of x, which means if you take the input, what is the rate of change at that point? What is that m value? So go from -2 to -4. And this is the rule that lets us calculate for any expression what is the value that we're getting out. So for example, for 2x to the 3, you bring the 3 out front, take the rest, and then just decrease the exponent by 1. That's what the power rule says. We did a bunch of examples. We talked about the sum rule, which just says, hey, if you can't combine like expressions, just take the derivative of each expression individually. And that's where we left off. Is that cool? Not too bad? Really bad? Horrendously bad? I don't know. What do you guys think?
Understandable.
Understandable. You know, I'll definitely link off to the resources so that if you want to get a deeper understanding, then you can slow it down, rewind, and of course you have these recordings to watch over again. So there is one last key rule we need to know about, and that is it. Then we are done. However, this rule is really important. This rule is the foundation of something which I think you guys have heard about if you're into AI. It is the foundation of backpropagation. Now, here's the thing. Backpropagation, like this algorithm, is just like don't stop using the chain rule ever. That is literally backpropagation. So this rule that we're about to learn, backpropagation just says just keep doing this forever. That is it. That is backpropagation. All right? So if you understand this, backpropagation, you can understand because it's just like do this a billion times. That is it. Sounds good? If you've never heard of the term backpropagation, do not worry. In 2 episodes, you will know. In 2 episodes. I shouldn't call these episodes sessions, whatever. So let's get into it. Now the chain rule, it's easier to understand the formal proof. You just need to know this key thing, this weird thing called limits. Again, I was going to teach it to you, but time issues. So I will definitely link off to a video. However, just like I did here, I didn't give you the formal proof of why the sum rule is true. I will give you like a rough proof, and it's a pretty understandable rough proof, just like this was pretty understandable. So don't worry, you'll be fine. So what I need to do for the chain rule is I need to get my scroll wheel to cooperate with me, which doesn't seem to be happening. So we're just gonna use these buttons. But after that, here's what we're gonna do. I'm gonna define 3 equations, okay? Here are the 3 equations. Oh, actually 2 equations. So let's say you have an equation that says z is equal to 4y squared. Okay, so this is a variable and it relates to another variable. However, y itself, it's made up of another variable. So it's like z is equal to 4y squared and y itself is equal to 2x. So you have like this equation is kind of embedded within this other equation. Yeah? I want you to visualize this for a second. Okay? So we have three knobs here for x, y, and z. Okay? So x, if you move it in some direction, so let's say you go from x is equal to 1 to x is equal to 2, it's going to change y, right? So let's say like you go from x is equal to 1 and x equals to, uh, if x is equal to 1 and y is equal to 2x, then you know y was 2. However, if you increase x, now y increases as well, yeah? So let's say like knob number 2 moves in this direction. However, hey, you just changed x, and that just caused a change in y. However, y is related to z. So it's like a ripple effect. So now it's like, okay, well, x changed, and then y changed, so now z is changing. And remember, calculus is about the rate of change. Hey, that's like four changes in one sentence. That is a lot of changes. All right? So like imagine real life context. Um, imagine, okay, x is your height. Your height is related to y, which is the size of shoe that you wear. And your size of shoe is related to z, which is the spacing between your steps, the stride length you have. So it's like if you increase x, then y changes. So if you increase your height, then your shoe size changes. And if you increase your shoe size, then your stride length changes. Yeah? You see? All of these variables interconnected. That's the way the world works. So here's what we want to do. Here's what we did last time. Okay, we said a derivative is how much does the output change with a tiny change in the input? So here we had a simple relationship. Okay, you change x, f of x changes. If you change x, the output changes. However, way down here, something has changed now. If we change x, it's not just that z changes. If we change x, first y changes, and then because y changes, then z changes. Comprendo? Yeah? So what we're looking for is dz by dx, where this is the output, yeah? And this is the input. I sounded way too happy when I said that. I don't know why. Okay, this is the output, this is the input. We want, okay, with a tiny change in x, dx, how much does y, well, in this case, how much does z change? So up above, we had examples that were like, okay, with a tiny change in x, how much does y change? Because in this case, x was the input, y was the output, yeah? Now it's no longer the case that x is the input, y is the output. Now we're saying x is the input and z is the output. And remember, this just means tiny change, dz by dx. So we're saying, okay, if we move the knob here, x in one direction, how much does y change? And as a result, how much does z change? Is that making sense? You get the question we're asking? So now this is a little bit hard for us to do because, you know, we can't just say, okay, I moved x, you know, by 1 and now I can just directly figure out what the output is because like we have this annoying y in the middle. We can't just go from x to z. So this is a bit hard for us. How do we figure this out when the outputs and inputs aren't directly related? This is what the chain rule helps us do. So here's what we're going to do. We're going to break it down, okay? So instead of going, okay, we got to jump right from X to Z, what we're going to try and do is we're going to break it down. So if we want to figure out, if we change X a little bit, how much does Z change? We're first going to figure out, okay, per unit of change in Z, Y, what is the unit of change in Z? Okay, so if we change this Y a little bit, how much does Z change? That's the output, that's the input. Yeah? And also we're going to figure out, okay, per unit of change in X, how much does Y change? So that's the output, that's the input. So first we're figuring out, okay, I move this in this direction, how much does Y change? And then once we figured out how much Y changes, well, per unit of change of Y, how much does Z change? Is this making sense? So our goal is, remember, get from small change in X, how much does small change in Z happen? So dz by dx, that's our goal. We want to figure out an expression for this. And the two pieces of information we have are how much there is a change related in Y from Z, yeah? And then per unit of change in X, how much does Y change? So we can go from here and here, yeah? We have these two key pieces of information. We got to figure out how do we relate them together so that we can figure out the end change, dz by dx. Is that cool? Is this making sense? Any questions? All right, so here's what I'm going to do. I'm going to try and pretend that I don't have these like weird d's over here. Because remember, what this says is like a tiny change in z, right? What if we did the same exact thing, except instead of dz by dx, we just had z over x? So instead of taking the tiny change in z and the tiny change in x, or a tiny change in z relative to a tiny change in y, we're just saying z over x, z over y, y over x. We're trying to figure out how do we get this given these two pieces of information. There is a nice convenient space here, don't you think? Just waiting for me to write something in there. What possible thing could I want to write in here? Aditya, you have an idea?
Multiplication. If you
Heck yeah.
multiply, the y cancels out, so it's z over x. Z
That
over
is
x is
correct.
equal to z over x.
So if we add a multiplication sign here, y and y cancel out, and you're just left with z over x. Yeah, z over x. Literally the same thing here. So if we want dz by dx, and we have like this inconvenient y in the middle, we can just multiply these two things together and say dy cancels out. So we're left with dz by dx. And remember that kind of makes sense, right? Because it's like, okay, you know, it's a little bit like you have like a snowball rolling down a hill, right? And it hits another snowball, right? So it's like, okay, x starts rolling down the hill. There's a change in x. Then it hits y. Then y starts changing and it hits z. And now z starts changing. The multiplication, not only does it let us cancel out these dy terms, it's kind of like, okay, this changes a bit, then that changes a bit, that changes a bit. So at each step, at each equation, all we're doing is we're taking, okay, what is the output of this relative to the input of that? Yeah, dz by dy. And then for the next one, we just keep doing the same thing. Okay, what is dy by dx? And then if we had more equations, we could keep doing the same thing still. And in the end, we just multiply them together and we're like, okay, if we're multiplying, that's kind of like we're aggregating together all of the changes. So this is a tiny change, this is a tiny change. And in the end, all the tiny changes multiply together so that we can figure out what the initial change to the end change is. Making sense? Sorry, you don't need to nod just because it makes sense to me. Does it make sense to you? Yes, it makes sense to me. Um, does it make sense to you? All right. So in general, let me write out the chain rule. The chain rule basically says if we have a set of equations where A is equal to something something B dot 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 B, B is equal to something 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 C, C is equal to something 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 D. That's too many dots, whatever. Um, and you could keep going on. If you want to figure out, okay, per unit of change of, like, let's say you make a tiny change in D. Oh, maybe I shouldn't use D. Oops. E. Let's call it E. D, E. So for a tiny change in E, how much is A affected? The A. If we want to figure that out, we can just go, okay, dA by dE, that's dA by dB, yeah? Output of first, input of first, times dB by dC, yeah? Output of second, input of second, times dC over, yeah, that's why I changed it from D to E, dC to dE, not dC to dd. This is the chain rule. Does it make sense? Any questions? All right. Are you guys ready to wrap up? Bring it all to completion.
I have one question.
Mm-hmm.
So, like, it's gonna be like one tangent line is equal to another tangent line times another tangent line times another tangent line, right?
Graphically, that's a good question. So it's going to be not the tangent line, but the slope of the tangent line. So this, like, it won't be a line times a line. It will be the slope of this line, which is a number, right? Times another number times another number. However, in this case, I prefer to think of it in terms of this definition. How much does the output change with a tiny change in input? It's more useful in machine learning, but at the end of the day, the rate of change, remember, is just a number. And at the end of the day, we're just multiplying together a few numbers. Does that answer your question?
Yeah, that answers my question.
All right. Aditya, do you have a question?
I learned a lot. I know I understand it, but then I need to, like, I don't know, connect all the dots still in
For
my brain.
sure.
So
Yeah,
I might have more questions.
that's cool. 100%. You can message me anytime afterwards. Plus, rewatching the recording helps. Plus, I'm going to make sure to link all the Khan Academy videos you could ever need in the description. So hopefully, the second time through, you'll be able to piece together a few of the dots. No, there's one last thing I gotta introduce to you. I'm sorry, I know so much content. Um, but it's not hard. So the last thing I gotta introduce to you is partial derivatives, which just mean how do I take the derivative of an equation like this, where you don't just have like one variable in an equation. So it's not like m is equal to 2n. Instead, it's like m is equal to n over p. So you have two variables that both affect one variable. Because if p goes up, then m goes down, because it's being divided by a larger number. If n goes up, if n goes up, m goes up, because it's being multiplied by a larger number. Does that make sense? So both of these variables affect this one variable. So what partial derivatives does is it tries to isolate for the effects of one variable, right? So let's say, for example, you want to figure out how fast you run, okay? Both your weight and your height affect how fast you run. So you want to figure out, okay, how much does gaining a pound, how much does that affect my running speed? Well, you got to isolate for that. So you got to figure out, okay, let's just set aside the height for a second. If we just focus on the weight, how much does a tiny change in my weight affect a tiny change in my running speed? Is that making sense? This is different from the equations we had up here, where it was like, okay, if we have one variable that is related to one variable, but that variable is made of another variable. This one's like, okay, we have one variable that is related to two other variables, or it could be many others. It could be many other variables. Making sense? So the way that we say this, it's not actually d by dm, so dm by dp. The way we say this is this special Greek symbol, which is called del or partial. So we say partial m by partial p. And what it's saying is like, what is the partial influence of p, a tiny change in p, to m? The reason it's a partial influence is because like there's other variables involved. This is like many of the problems AI tries to work with, you know, real world issues. There's lots of variables involved. You got to isolate for the effects of one or the other. So this is the idea of partial derivatives. We want to figure out how do we isolate for one of these variables, so in this case p. So we say partial m by partial p. How does a tiny change in p affect a tiny change in m? Does that problem formulation sound good, what we're trying to do?
Yeah.
Arjun?
Can you say the partial derivative thing in the tangent line definition of the derivative?
Yeah, so let's say you have a tangent line. That's a good question, by the way. Connecting the two definitions, that's good. So let's say you have a tangent line that is determined by this equation. So this is a line, right? So lines have the equation that we talked about last time, y equals mx plus b. So let's say we have y is equal to mx plus b, and that denotes this line's equation, yeah? It denotes the equation of this line. So what is the effect of m on this n value, and what is the effect of b? So let's say we have partial y by partial b. That's what it's saying. Okay, set aside the influence of m. How much does b affect the final output value? Yeah? All right. Does that answer your question?
Yeah, it does. Thank you.
All right. So that is the problem formulation. Here's how we're going to visualize it. So instead of like just having one knob, you know, earlier I drew one knob. Okay, so this is like one lever. We're moving X back and forth, Y back and forth. Now it's like we can move P back and forth, and we can move N back and forth. It's like we could move, say, P a little bit this way, and we could move N a little bit that way, and we would get like a new point, a new combination of values here. So here's another point. And we want to figure out, okay, so we just made these moves. How much does M move? You know, it could move like a little bit to the right, for instance. So maybe M ends up moving like this in response to the changes we just made. Do you get the idea? So we're moving multiple things.
So we have to move n and p at the same time.
We don't have to, but we can. So we're just saying that these values, when the two of them move, then m moves, and we want to figure out, okay, what's the relationship? We don't have to move both. So let's say we just move like p. In this case, we're trying to figure out partial m by partial p. Again, that means tiny change in p and tiny change in m. So we can be like, okay, tiny change just in p, and now we have like a new value, but n hasn't changed. Yeah?
Yeah, so if you're gonna change both, would this like the partial m over partial p, that equation thing change?
Yeah, so that wouldn't be a partial derivative actually anymore, because in that case we weren't just changing one. That's just like a possibility. We could change both if we wanted to. But in this case, what we're actually going to do is we're actually going to pretend, okay, all of this n, all of these spaces with n, they're like blocked off. You cannot change n, okay? N has to stay at this value. Let's say n is equal to 2. And everything else is blocked off. So you can only move p. Yeah? So let's say like we're setting n is equal to 2. Is that making sense? The reason we're doing that is so we can isolate for the effects of p. We're saying, okay, set aside the height for now. I just want to look at the weight and figure out how much does the change in the weight affect m.
Yeah.
That was a very contemplative, yeah.
Yeah.
Aries, you're not convinced?
And I'm processing it.
Okay. Let me say it in simple language. Let me try. We want to figure out, we have these two variables that can affect one variable. So what we want to do is we want to isolate for the effects of just this variable that we're concerned about. We're going to figure out, okay, if we make a tiny change in p, how much does m change? So what we're going to do
Oh,
is we're going to lock n in place. We're going to say, no, cannot change like all of these other values. We're going to set n is equal to 2, for example. Yeah? And then we can just isolate for the effects of p. What happens when we move from this value of p, say 1, to this value of p, say 3. Or if we're like looking at even tinier changes, 1 to like maybe 0.0000001, 1.0001. Yeah,
yeah.
Aris? All right. So if we did that, it's kind of like we're saying our equation is m. We're saying we're going to freeze, we're going to lock the two in place. It's kind of like we're saying m is equal to 2 over p. Mm, like so. So we're saying like n, we're going to lock it to a constant, yeah? That's how we solve partial derivatives. We just pretend that the other value, it's a constant. We don't have to worry about it because right now we're dealing with something else. So again, partial, not d, just a notation thing. We're going to say partial m over partial p. We're going to use this equation, remember, because we needed to use our exponential rules. So we're treating n like a constant. We're going to say it's like, it's 2p to the negative 1. How would you differentiate? That's what we call like taking the derivative. How would you differentiate between, how would you differentiate this expression? So what's the derivative of 2p to the negative 1?
Um. Uh.
Two
It's
times.
-1 times 2p to the
Yep,
power of -2.
you got it. So you bring the coefficient down, and then you take whatever expression you had, you put it in brackets, and you reduce the exponents by 1, so from -1 to -2. One thing that I'm going to do is, remember, we're just assuming n is equal to 2, n could be anything really, so we still call it n. It's just like we're treating it as a constant. Okay, we're just treating it as a constant. We're pretending it's a constant. Really, n may not be equal to 2. Making sense? Let's try another example just to
Quick question. On the example we just did,
mhm.
should there be a 2?
Where?
Uh, so like 2p to the power of -2.
Yeah, so remember
Oh,
n is
right.
equal to 2.
Yeah,
That's just our
okay.
assumption. Really, n could be any constant value. So that's just why we wrote n. We're just pretending n is equal to a constant.
Right, got it.
So I'll show another equation. I'll use x's and y's because it's more familiar. Sorry, Aries.
So, going back to example again, if you actually want to solve the derivative of, if you actually want to solve for p, then you're gonna have to set n for a constant. So in that equation.
Yeah.
Okay. Okay, got it. Thanks.
So whatever constant n is at the time, it's going to be multiplied by p. Remember, these are just expressions for us to plug numbers into, right? That's why we calculated all the way up here, f prime of x, or dy by dx, so that we could create a new expression that's like, okay, from x squared we go to 2x, so that we could plug in values of x. We could plug in the values of the variables and get output numbers, which are the rates of change at the 1 point. So it's still the same thing. We just gotta plug in more values, more variables. I'll do one last example for tonight. So let's say y is equal to ab squared. We wanna say, what is partial y by partial, let's go for a. Okay, so if we make a tiny change in a, how much does y change? To be able to do that, we gotta assume b squared is like a constant. So imagine like b was equal to 2. So it would be 2 squared equals 4. So I'm actually gonna rewrite it like that. So y is equal to, let me make b squared a constant. All right, that's why I'm putting it out front. We're treating it like a coefficient, just like a real number, like 4 or something. B squared times a. Remember, this is a to the 1. Any brave people want to differentiate this? So imagine b squared was a constant. How would you find the derivative?
1 times
Yeah.
b to the power of 2, a to the power of 0, which is basically b to the power of 2.
Yep. So again, what we did here was we took the 1 from up front, brought it here. Then we took the expression that we saw, b squared a. Remember, this is like constant, so it could be like a number like 4. And then we went, okay, we got to reduce this by 1, so we get a to the 0, not a to the 1. This, as we said, was 1. So partial y by partial a in the end, it just becomes b squared. That is the answer. And remember what the real life context says? This is the slope of the equation at that point. So we're going to substitute in some value of b, and we're going to get the slope of just that point. Making sense?
I have a question.
Mm-hmm.
Why is it 1 at the beginning of the bracket? Shouldn't it be 2 because it's b squared or no?
Remember, this is like a constant. So for example, let's say the constant value of b was b equals 2. This would be like 4.
Yeah.
So when we're differentiating 4a to the 1, then the 1 is the exponent. We bring the exponent down. And I can color code it right like this. 1 is the exponent, we brought it down. And the rest of the expression, we just multiply it in and then reduce the value of the exponent by 1. So this is being treated like it's a number, not like a variable, like a number.
So we're isolating the variable b to find a.
We're actually,
Or yeah, the other way around. You're giving a
yeah,
value to b to isolate a.
isolate for the effects of a. We're saying
Okay.
if a tiny change in a occurs, what's the tiny change in y that's going to occur?
Yeah.
That is the meaning of this question in mathematical language.
Okay. Yeah. Thank you.
Make sense? So I know this was a big lesson. As I said, this was the hardest lesson. And congratulations, you just survived through it. So don't worry, it only gets easier from here. What I'm going to do is I'm going to post all of the recordings. I highly suggest you review them. And if you don't like me talking, you're just like, oh my gosh, this guy just goes on and on and on. I will definitely leave like Khan Academy links in the recordings, including the links to all of these ideas. If you want to know what is the real explanation for, why is this rule true? So I know it's hard. I know it's a big lesson, but I hope that if nothing, you just appreciate the power of this tiny statement, how powerful derivatives can be. Remember all the key examples, all the examples from the first video we took. Aditya, last question. We got 2 minutes.
Yes, I have a quick question. Could you zoom out so like I can see the entire thing? I'm just curious. Woo!
We
Did we do that all today?
did that all today.
Oh my god.
So,
Question about the chain rule.
yeah, sure.
For the chain rule, we're so let's say we have like 3 levels, right? So would that be like 3 dimensions?
Okay, so here I wouldn't think of it as dimensions. The reason it makes sense over here as dimensions is because like you can change both of these in one equation. With the chain rule, I'd rather think of it as like separate graphs. Okay? So like one graph is x versus y. All right? So maybe you have like some pattern here. And then another graph is like y versus z. And then you have like another pattern here. Make sense?
Yeah.
All right. Well, we have under a minute, so unfortunately I will have to end here. However, feel free to message me with any questions you have. And again, the link will be posted. You can review this anytime.